So what happens if we have more than one pi bond reacting? Where should our hydrogen add? So we've got two different structures here, both of them with two different pi bonds or two pi bonds, and we want to be able to evaluate where our hydrogen should be adding to this. So let's go ahead and look at the leftmost structure and decide. If we were to go through and evaluate this, hopefully you'd be able to acknowledge that the now red pi bond and the blue pi bond should establish a regiochemistry where we get positive and negative, and partially positive and partially negative. There is the potential where those invert. We talked about why that doesn't make sense earlier on. We'll see those potentials show up in a little bit, but we should be able to address that this is going to be the best system. So let's go ahead and react the red pi bond first. If we were to go through and react this with an H+, we would expect our hydrogen to go here, which would mean we'd be left with the carbocation out there. Okay, remember there was still a hydrogen there that is still there. The pi bond is still present, or the blue pi bond is still present, and we'd get that as a potential product. We could just as easily have had the other pi bond react. So again, we still have the red pi bond now. And when we go through and do that one, we would place our new hydrogen at the tail end. I kind of feel like I added a carbon. Nope. There's that new hydrogen. Remember, we still had two hydrogens out there, and we'd be left with a carbocation here. So in deciding between these two, which one is the more likely for the pi bond or to pick up the hydrogen? One analysis that we could use would be that the blue one should react first because it's the most accessible, so it's the most likely to occur. Okay, so if we're going to make that argument, what we're saying, there's our reactant, is that the blue one is, pause. Sorry about that. Our blue one was more likely to react because it's on the outside. That would mean its activation barrier is a lower reaction than the red one. So we'd be making the statement something along these lines, perhaps something along these lines. Okay, with that being a product. And then we could connect our diagram out and be making something along those statements. But if we remember, our transition state, which is going to determine the speed of our reaction, is dictated based off the one that is closest in energy, be it reactant or product. Our product is the closer one in energy. So what we can go through and do is take a look at the products and say, well, which one is going to be lower in energy? Well, the red one is a tertiary carbocation. The black or the blue one, black and or blue, depending on how you want to look at it, is the secondary, which means our red product is actually lower in energy than our blue product. So if we were to connect out our energy diagram, the red one is actually going to have a lower activation barrier. This is going to be due largely to our, oh man, I'm tired. Due largely to the kinetics or thermodynamics of our reaction. That lower energy product drops that transition state, and we end up seeing the red one predominate. Okay, so even though the blue one might appear to be more accessible, the red one generates a more stable product, and because of that, that has a larger effect on the drop of the transition state, and we see the red one or the red reaction win out over the blue reaction. Which means if we look at our product, we just see that one product. Okay, and we would end up with this guy, which could then go through its chemistries. You might go through and say, well, we've got a carbocation. Shouldn't we be thinking about rearrangements? Yes, we should, but it's a tertiary carbocation. There's no easy rearrangement to do that would actually make it more stable. That's why I had to pick a structure that had enough carbons in between to ensure that even if we did a rearrangement, we wouldn't be introducing resonance stabilization. Okay, so those two pi bonds are very distinct and different from each other, and it prevents any kind of internal messing with that, and really all we're seeing is them effectively acting as two separate bonds. What happens when we go through and look at the other structure? Well, we could probably go through and make the same arguments, and here we might notice that we've got an issue, because we would put our partial positives kind of butting up against each other. Okay, and that's going to be potentially problematic. Okay, but before we even get into that, we could simplify this out and say, well, which pi bond do I want to react? I don't have to deal with the positive negatives yet. I could go through and say, well, due to the line of symmetry, they are identical. It doesn't matter which one I react. They're going to be the same. Okay, so we could go through and draw out a product where we put our hydrogen on the more positive, the more negative carbon, and we now have our carbocation. The pi bond on the other one is still available. And now we could potentially run the reaction, or continue to run our reaction. Okay, but notice that that pi bond is one sigma bond away. We have the potential for resonance. Why does this become important? Well, that pi bond has now apparently moved locations, and if we were to go through and react these in a subsequent step, say add a nucleophile, because we were doing electrophilic addition, we would end up with different products. Our nucleophile would end up doing the addition at a different spot, which drastically changes our end results. So when we're looking at more than one pi bond, we need to be thinking about number one, is there a difference between our pi bonds? And then we need to be thinking about forming the most stable carbocations. Why do we need carbocations? Well, that's what we talked about in our earlier electrophilic addition reactions. The acid has to be neutralized first. We got to make a stable carbocation. Okay, so conjugation changes it, and we now get the potential for two products. In separate or if they aren't conjugated, I can't remember the word, but if they aren't conjugated, we're going to end up reacting to make the most stable intermediate possible, which means usually our tertiary carbocation systems. Okay, I do apologize because what this slide shows is a whole bunch of products for that leftmost one. And again, really what that's trying to show is all of the possible places that our hydrogens could potentially go. Where we're saying we've got our red hydrogen or our red pi bond and our blue pi bond reacting. As we discussed, it doesn't make sense to have the blue pi bond react because we're looking at secondary or primary results, which means our lower instability than our tertiary or secondary. Between the tertiary and the secondary, we would expect the tertiary to form because the tertiary carbocation is more stable, which means of all of the possible reactions we could have run there, we really only got one. When they were conjugated, we ended up with two possible intermediates, which means two possible products. Okay, so that conjugation raises a whole nother can of worms. You jerk, I thought I had that shown there, and I inconveniently don't. That carbocation is more stable than the first one, or than the one I've crossed out, and that one has that resonance stabilization. That resonance introduces another structure, and that other structure or another intermediate can now potentially react. Okay, so if we were going to try and figure out what's going on with that, we're going to have to think about looking at an energy diagram and trying to predict this out. This energy diagram is showing, or when we're going to look at this energy diagram, we're going to show these two species, which are technically the same species. We're going to show them as two independent wells in our energy diagram, or two independent pieces. So if we were to go through and activate this, we've got a reactant, we've got intermediate 1, intermediate 2, and we would end with product 1 and product 2. What I'd like you to go through and do is draw an energy diagram to represent these two reactions in the same space. Okay, so we've shown some overlapping energy diagrams. That's what I want you to take a second to go through and build. So hit the space bar, click the picture, pause the video, spend some time to draw out an energy diagram of your own. Hopefully you've got an energy diagram. Both of them are going to be starting with a reactant, so we'll go ahead and pick that there. I'm going to pick pathway 1, or what we'll call 1. Intermediate 1 has to be higher in energy than our reactant because it has that carbocation, so there's intermediate 1, okay, somewhere higher than energy. We move to my product, I'll have product 1. That product 1 should be lower in energy than my intermediate, and it should be lower in energy than my reactant because I've lost a pi bond. So there's product 1. I could now go through and connect these out, and we would end with our energy diagram. So that would be one representative energy diagram. So you should have drawn the second one, but just in case you didn't have an opportunity to draw the second one because you weren't sure where to go ahead and draw the second one on here. And so yeah, pause and draw it. Okay, so now when we move through, I want to take a look intermediate 1 versus intermediate 2. I need to draw intermediate 2 in here, and it definitely needs to be higher than energy than reactant, but should it be higher than intermediate 1 or lower than intermediate 1? Well, intermediate 1 is reactive because of the carbocation. That is a secondary carbocation. Intermediate 2 is reactive for the same reason. It's a carbocation, but that one's primary, which would suggest that intermediate 2 should actually be higher in energy than intermediate 1. Okay, so as we start to draw this out, of course I've color-coded this the opposite of how I wanted to, but oh well. And we've got our first step. Based off of that first step, we would potentially expect product 1 to dominate our end results here because it's a faster first step. But before we start jumping to conclusions, let's take a look at the placement of product 2 in comparison to product 1. So in this, I don't want you thinking about anything else. What you are looking at is just those two structures. What makes those two structures reactive? Well, it's the pi bond. Where is the pi bond more stable? According to Zaitsev, the more substituted pi bond is more stable, which means P2 is our more stable product. So we can now go back to our energy diagram and we would be drawing P2 underneath P1, which means when we continue out our energy diagram, we would get something along those lines. This introduces a bit of a dilemma. If I look at just the energy of the products, which product should be the major, quote-unquote, product? Well, the major should be the lower energy one, so it'll be product 2. If I go through and look at my reactants going to intermediates, which of those should be my major product? Well, pathway 1 results in a faster intermediate, so I would expect intermediate 1 to form faster. And if it forms faster, I would then expect product 1 to dominate. Okay, you'll notice that where we're making this analysis is in different aspects of our energy diagram. Okay, the red area I'm making in reference to the activation area of my energy diagram. We're talking about that as a kinetic argument. If we look at the products, we're only concerned about the energy difference between those. That is now a thermodynamic discussion. So depending on the conditions of our reaction, we could favor one of these or the other. Okay, and that's where this becomes an interesting question. Both of these can be major products, but we have to be cognizant of the reaction conditions that forms them. This balance or this interplay between kinetics and thermodynamics shows up in virtually every single reaction we run in second semester. And it really only sort of rears its head here when we're looking at these conjugated alkenes and how they react differently. But what we're really trying to address is this concept between kinetic and thermodynamic. So let's consider those reaction conditions. Let's say we run this reaction freezing cold. Okay, what happens if we run the reaction freezing cold? Which product would I expect to form first? Okay, so it's freezing cold. Which product would I expect? Well, if it's cold, I don't have a lot of energy, which means I can really only clear the smallest activation barrier, which means the product that I'm going to get first will be product 1. Because it is cold, I also can't reverse this reaction very easily. So under those cold conditions, I don't reverse the reaction. I can only form product 1 and I'm done. Okay? But what happens if I heat it up? What happens if I make this hot? Okay? What product do I form first? Well, if it's hot, I'm going to clear the easiest activation barrier, which is still to form product 1. So the product I get is still product 1. But remember, it's hot. What does that heat do? That changes that non-reversible reaction, and it now makes it reversible. We now have enough energy to clear the reverse reaction. And for those who are saying, well, that doesn't matter, I'm still going to form the reactant and then still go over to product 1. You're right. But a small percentage of it will make it to intermediate 2. Once it clears the intermediate 2, it now makes it to product 2. Product 2 being lower in energy than product 1 will always be non-reversible or irreversible, which means we are looking at two mechanisms or two equilibriums at interplay with each other. And if I have the reaction hot and for long enough, product 1 will irreversibly shift to form product 2. So the product I get at the end of that will be product 2. And what we're looking at here is how temperature can affect that reaction. And that's really neat and fascinating. If you really want to dig into this further, which I'm sure you don't, but if you want to and aren't taking second semester OChem, there are some videos that I've got on my channel labeled as kinetic and thermodynamic, and they really kind of talk about this interplay between kinetics and thermodynamics as far as determining products go with both our conditions, cold and heat, and as far as reagents. Sometimes reagents that we use will force a reaction to be irreversible, and that can make things a little more interesting. And I believe with that we've hit the end of what I wanted to get out of this. We'll go ahead and advance just to make sure, and yeah, sure enough, we're good on that. So that's our big story for our conjugated alkenes. We have to consider resonance, and we have to be wondering about or thinking about this kinetic versus thermodynamic system. Sometimes they're different, sometimes they're the same. Really, it just comes down to looking at that energy diagram.